Okay, so today what we're going to do is we're taking a weak acid and we're going to titrate it with a strong base. Now, before we get into this, there's important to remember that every single titration, every single one of them deals with two parts. Number one, do the stoich. What that means is we've got to take care of whatever the strong base or strong acid is being added in moles before we go ahead and do the equilibrium. So this is no different in that we're given a problem, and so let's keep those there, but let's take a look. They're giving us propionic acid, and we're titrating it with NaOH. In other words, this NaOH is going to chomp down on this propionic acid until it's either going to use up all the propionic acid or all the NaOH is going to be used up. One of the two things. So the first part of our problem, we have to set up an equation to show what is actually going on here. Now, I do not want to write this over and over again. And because we know that there's only one hydrogen on this, we can do our fancy little rearrangement of equation and call it H prop, the propionic acid standing for this C2H3O, whatever, and the hydrogen on the end of it. And what we're going to do in our first step, which is the stoichiometry step, is we are going to throw in the NaOH into it. Now, what's important is that the Na in this NaOH, that is a spectator ion. We're not going to use that at all, but we are going to use the OH minus. And when the OH minus connects with the H prop, it's going to pull it off, and we're going to end up with propionic minus plus H2O, which is a liquid. So the states of matter are aqueous, all kinds of aqueous, and then H2O, which is a liquid. Now, the other really, really important equation we have to use is we have to be able to manipulate molarity and is equal to moles per volume. So since our first step, the stoichiometry, is always done in moles or millimoles, whatever is easier for you to do, we want to rearrange this equation right here to get our moles by itself. And so simply enough, when we rearrange this, we end up with molarity times volume equals moles. So what does that allow us to do here? Well, we know what our initial volume is of the propionic acid, and we know what its molarity is. So if we multiply the molarity by its volume, we're going to end up with the moles or the millimoles. Now, since we're dealing with milliliters right here, I'm going to keep it in milliliters and we're going to end up with millimoles. So I'm going to do this over to the side, and then we're going to plug it back in. So realize all we're going to do is do the figuring out for the millimoles of this and also for the millimoles of this. Remember, we have 1 molar and we're adding 176.7 milliliters to it. So let's do this over here. And first things first, we know that we have 0.72 molar, so we're going to write down here 0.7200 molar, and we're going to multiply that by the volume, which is 204.7 milliliters, and that's going to end up with giving us our millimoles, milli-N, or millimoles. Now, when we actually do the math on that, we're going to end up with 147.384 millimoles. That's the number of millimoles that we have of our H prop. So here with our initial, we're going to have 147.384 millimoles. Now we're going to have to figure out what our initial amount is of our OH. So this right here was for our H prop. Oops. And now we're going to do the same thing for our NaOH. But in reality, we know that we're just doing it for our OH minus. So let's take a look at what they've given us here. They've given us 1 molar, which we love so much, and they're giving us 176.7 milliliters. So that makes our calculation pretty straightforward. We're going to take our 1 point, I don't really want to do it in a different color. So let's get rid of it. we're going to write, boy, oh boy, one of those days, right? We're going to write 1.000 molar, and we're going to multiply that by 176.7 milliliters. And we multiply those two together, we end up with 176.7 millimoles. Now this is really, really important because when we go back to our equilibrium expression, now right here we have 176.7 millimoles. Now, when we're starting off this problem, remember all that we had was the propionic acid, and to that propionic acid we're adding OH minus. We have no of the prop minus and the water, well, we don't really care about because it doesn't do anything for us. So over here we have 0, and then we're just going to ignore this because it's a liquid, doesn't impact our equilibrium. Now what we do know is that our change is going to be whatever one of these two things runs out first. So if we take a look at this, isn't this a 1-to-1-to-1 relationship? So if I have 147 millimoles here and I have 176.7 millimoles here, when I subtract them from each other, I'm going to subtract the smallest one, which is this. I'm going to lose 147.384 from here, and I'm going to lose 147.384 from here, and I'm going to gain 147.384 here. Now, what is the net result at the end? Now, this looks suspiciously like our ice problem, but in reality, it's initial change and end. We're going to have 0 of this. When we subtract these two from each other, we're going to end up with 0.029. Try that one again. 29.3160 millimoles. I want to keep us with millimoles here, so we're going to scribble this out here. 29.31, and then down here, when we add these two together, we're going to end up with 147.384 millimoles. So here's what's really, really important in this. When we take a look at our problem, we have none of the original acids left. In other words, we've put so much base into our titration that it overran the weak acid. So what we do have left is we have 29.3160 millimoles of strong base. We also have the conjugate 147.384 millimoles of propionic acid. But here's the thing. We know that propionic acid, if we were to throw that into water and react, it would produce a little bit of OH minuses. But these are pure OH minuses. So we ignore the prop. We just look at the OH minus right here, and we discover that we have 29.316 millimoles. Now, here's what's really important, is that when we do this, we've added together our two volumes. So we have in here, we have the original H prop, right? And to that, we added in a bunch of OH minus. We have to account for the new volume because when the only thing we have left is our OH minus, what we want to do is figure out its molarity, and then if we take the negative log of that, we're going to know our POH and then our pH, because that's the only thing that's left in solution. So we have to add the two volumes together. Now, if we take a look, we had 176.7 here, and we have 204.7 here. So if we add the two of them together, and we divide this into it. So essentially what we're going to do is we're going to take this, and we're going to divide it by 204.7 milliliters plus 176.7 milliliters combined. You can do it right here. It doesn't really matter where you do it. But when we do this together, we end up with 0.076864 molar. Now, if you're wondering how we got that, remember, if we rearrange our equation and we take a look at this right here, molarity is equal to moles divided by volume. And if we take our millimoles and divide them by milliliters, the millis cancel out, and we end up with our moles per liter, and that's equal to molarity. So this is our molarity, but it's our molarity of our OH minus concentration. Now, the problem is asking us for what is the final pH, calculate the pH of the solution. Well, all we have left in the solution here is OH minus. So we can do this one of two ways. It really depends on which you feel more comfortable with. Some people like to take the negative log of this and then subtract from 14. Or you can take this equation right here, changing our H plus concentration times OH minus concentration equals 1.0 times 10 to the negative 14. So I'm going to do that. I'm going to take this right here and I'm going to plug it in for my OH minus concentration. And essentially what we're going to do is we're going to divide this number right here by our OH, this number right here by our OH. So our H plus concentration is going to be equal to 1.0 times 10 to the negative 14, all divided by 0.076864. I'm keeping all these numbers in there, all the significant figures. We're going to wait till the very end to mess with that. And when we do the math on this, my H plus concentration is going to be equal to 1.31401 times 10 to the negative 13 molar. And we would expect that we'd have incredibly small amount of H plus because we have only strong base in there. And if we take the pH, wouldn't that be the negative log of this 1.31401 times 10 to the negative 13? And when we do that, we end up with 12.8814. That is our pH for this problem. Now, normally what we would do is we would look back at our original problem here and we would take a look and see what is the least number of significant figures we used. Here we have 4, here we have 4. They gave us the pKa right here, and that only has 2 significant figures, but did we use the pKa in this problem at all? Nope, so we don't care about that. And here we have 4. So in reality, and we have 4 right here, in reality, we would solve our answer to 4 decimal places, but here they specifically said do it to 2 decimal places. If it was 4, this would be our answer, but since they're only asking us for 2, we have to cut this off right here, and our final answer is going to end up being 12.88. As you try more of these, hopefully it'll become a little bit easier. I'd welcome you to watch the video I put on how to do titrations, particularly with weak acids and strong bases. Hopefully this has been helpful.